And we are now on record. So, welcome everyone. So yesterday we talked about the central limit theorem a little bit. So here we see that if we have, I just pulled it up here to show that if we have a random variable with a known mean and our known expected value and variance, we can calculate, we take a sample, that x bar there meaning the average, sample average or sample mean, and then we normalize it. So we subtract from that the expected value and divide by the standard deviation divided by the square root of n, where n is the sample size. Then we get what is called the standardized sample mean. And it turns out that the standardized sample mean approaches in its distribution the 0-1 normal distribution. And this is a justification for using those normal distribution type results that we use in our analysis. And like I meant, I'm not going to go through all the warnings that I gave last time about using the central limit theorem. You all know that, so we're going to just go ahead and talk about the practice here. So whenever this is still yesterday, so whenever we are comfortable with assuming that a variable is close enough to be normally distributed, we denote it like this. It conforms to pretty much. This is the dot there, meaning that we are approximating x's distribution with a normal distribution, or x is as good as normally distributed. Here we had the elevator example. We talked about that, and I mentioned certain caveats about how the analysis goes. Today we must skip many of the examples because we are going to have a lot of things to talk about. I mentioned that the binomial distribution is pretty well approximated by the normal distribution for large n and reasonable p. So a rule of thumb, if np and n times 1 minus p are both greater than 5, then it's a pretty good approximation. The bigger this number is, then the better the approximation is. I mentioned that even in more general fashion, a sequence of independent random variables that are not defined in any pathological way will tend to be normally distributed. So how this more general version of the central limit theorem is often applied is that if there's a phenomenon that has many different factors that contribute to it, and these factors are independent of each other, then it will be pretty closely normally distributed. One such example might be the human height. So the height of a person in a given population is often pretty well normally distributed, at least when it comes to a couple of standard deviations from the mean. The reason being that there are so many factors that contribute to this independently, and so many other variables that contribute to height. So there's a diet, and diet varies from day to day. So you can think that the person eating randomly every day, what they eat has an effect on how tall they grow as a child, of course, as a child, what they eat. And, their genes, the genome is randomly distributed at least in some way, how much sunlight you get and so forth. So there are many contributing variables to how tall a person grows. So that's why the resulting curve the distribution will be resembling of normal distribution, at least when we are talking about values closer to the mean. And one thing I didn't mention yesterday about how the application of the central limit theorem goes is that the approximation gets better at the center more rapidly than it does around the edges. So what happens is that the approximations, if you use the normal distribution, it will approximate the phenomenon for smaller n, or even for the pathological cases for smaller n. The approximation will be pretty accurate when you're talking about things that happen at close to the mean. or close to the expected value. But the tails are where the problems lie. So if you're trying to assess the risk of very rare events, then central limit theorem may not be the one that you want to discuss. So it may give you too small probabilities of those events that are supposed to be rare. But for the probabilities associated with common events, events, so if we're talking about people's height, for instance, and we had that example where the people's height was normally distributed around, let's say, 174 centimeters, perhaps, or 165 for females or something like this. And if we're talking about which proportion of them are between a few centimeters of that, and we're talking about the probabilities, then those probabilities will be pretty accurate. But then you would probably expect that the normal distribution would give you the idea that no one or 1 in 1 billion is 190 centimeters tall, but there are several people who are that tall. So the rare events look rarer in the normal distribution approximation than in the real world. That's very often the case. I'm not going to go any more in depth in there, but that's the part where you need to be careful when you apply it. We talked about sample variance as well. I'm going to go here a little bit. We talked about, I think we went to this is where we stopped, and we showed that the expected value of the sample variance is in fact the same as the variance of the variable. This was under the assumption that we have a random variable, any kind of random variable, and if it has an actual variance, which is sigma squared, and we showed that the expected value of the sample variance as calculated by this formula here, which makes use of the sample variance here. And then this is the way we defined it, has the expected value, and we talked a little bit about that. The thing about sample variance is it doesn't follow the normal distribution for even large n, because it's clearly non-negative. I mean, if we have a very small variance of the random variable, then the sample variance could be, if you're very unlucky, the sample variance could have large values, but it cannot have values that are very small. Not smaller than 0, obviously. So we need another kind of a distribution, and it turns out there is a distribution which it will conform to, at least in some approximately. We talk about this. It's now here. I'm a little bit. How do you pronounce that? Is it he? How do you pronounce it? It's like the X in the word Mexico, right? That's the Latin. A Greek letter. I think it's called he. Squared distribution, or chi. Some people say chi. So it has a one parameter n, and we call it the degrees of freedom of this. And we say that this, okay, here's a typo. Glad I spotted that. I'll fix that later. So not X, W. We usually mark these by W. It shouldn't be X, it should be W. So W has the chi squared distribution, and it should have the parameter n. If it has the following density functions, I'm just going to fix that. So now it's fixed. So there's a chi squared distribution with parameter n. We mark it like this: W conforms to chi squared n. If it has the following density function, and this is the sort of density function that I would not recommend you try to memorize. It can be shown that, in fact, if you take n 0, if you take 0, 1 normal distribution, you take n instances of the 0, 1 distribution, take the squares of those and add them together. then what results is the chi-squared with degrees freedom n. I'm not going to go into detail here, but you can show that this is what happens to this variable, and that's what it will result in. It involves the use of the Euler gamma function here, and this goes very far beyond the scope of this course to prove that. So we're not going to go in depth, but this is a distribution that is used. It's something that we can only calculate numerically. It can be calculated numerically pretty easily, but by hand, no one is ever going to do that because it involves this kind of infinite integrals and all that. So it has a sample space of non-negative real numbers. And what it looks like is, it looks a little bit like, I mean, if you draw a graph, I didn't include the graph here, but if you draw a graph, it looks a little bit like the Poisson distributions graph or something like this, you know, but continuous, of course. All right, let's go. So here's an example. Let's say X has a chi-squared with degrees of freedom 14, and we need to find W1 and W2 such that the probability that this, again, here I have X and I mix these. Why do I mix these X and W's? I'm terribly sorry. You can probably see I didn't have time to proofread all my translations here. So we need the tail ends of 0.1 probabilities. And because the chi-squared distribution, I'm not going to claim that my drawing is in any way accurate, but let's say it looks something like this. So the distribution will tend to look something like this. That's roughly the shape of the chi-squared distribution. It will rise here and then it will have a long tail. The tail should be even longer here, but never mind. And we're looking for probabilities. We're looking for these tails. We're looking for these tails, W1 and W2, such that the you see, the probability is 0.1 that it's here, 0.1 that it's here. I'll give them in Moodle these tables for the chi-squared distribution later this week. We find the column that corresponds to this value and conclude that the value for W1 is 7.790 and the value for W2 is 21.064. Alternatively, with MATLAB, there is a chi-squared inv function which calculates the inverse of the chi-squared distribution and with the degrees of freedom, so it will give these results. 0.9 is because this is 1 minus 0.9, and then, you know, again, look, if we're looking for the cumulative distribution function, in order to get this part here, we can take 1 minus this part. And that's often the case how we calculated it, but then, you know, the software just gives you the cumulative distribution functions inverse. The thing about this is that for chi-squared distributed random variable, the expected value is n, the number of degrees of freedom, and variance is 2n. I said here that the proof is left as exercise. It's quite heavy on calculus. I'm kidding. I'm not going to make you do that because it's quite heavy on calculus, and I cut down on calculus on this course. I don't want that to be the burden that prevents you from doing it. So you can outsource the calculus to software and do that if you want to, but we don't have time or the energy to go through that heavy calculus here. Most of you will prefer to skip that. I do recommend for those who are interested in more advanced statistics and so forth to go ahead and do the analysis, but we are pressed for time as it is. So we need this distribution because of what? Well, the first of all, if we have n0, 1, so normally 0, 1 normally distributed variables, and n variables that are 0, 1 normally distributed, then the sum of their squares is chi squared n distributed. And also, if we have two chi squared distributed variables that are independent and formed as sum of squares of independent n0, 1 variables, like here, then their sum is chi squared n plus m, and if n is greater than m, then their difference is chi squared n minus m. So that's is that difference true? That may not be true. The difference might not be true because the sum of squares is always positive. That's probably, there's something wrong here. I'll have to double check this. Yeah, this is probably not true. This is true, however. Yeah, let's remove. I'm going to remove that part here because I'm not actually convinced that that's true. I don't know why it's there. I'm just going to remove that here because it's probably not true. I mean, just a sanity check. Why would it be? Right? If you have two of these variables, one has 2 degrees freedom, one has 1 degree of freedom. If you take a sample of the difference of those two, it could be negative. But even the 1 squared and 0, 1 squared, it can never be negative. So it's most definitely the difference is not. Yeah, it's not in the finished material. I know it's not in the finished material. I don't know where it came from. I must have added it by mistake from maybe it was another theorem that had some. I think it was the F distribution or something that had a difference, and now I just threw it in there and made a mistake. But good to point. Well, it's gone now, so I never said it, although it's on record that I did say it, but it was wrong. Okay, let's move on. As it happens is that if we have a sample of the variable n mu sigma squared, and the sample mean is bar x, and sample variance is calculated as s squared, then there are two things that happen. S squared and the bar x are independent. They're random variables and they are independent. This is highly important that the two are independent. It's not immediately obvious that they are independent because x bar is used in the calculation of s squared. But as random variables, the two are in fact independent, which is, I think, it kind of weird, but I think the proof is pretty hard. I've seen the proof, but I'm not going to claim that I understand how the proof goes, right? So it goes beyond me even. And if we calculate another statistic where we eliminate from s squared the factor that is divided, that it's divided by n minus 1, and then divide and normalize it by dividing it with the actual sample, and divide the sample variance by the actual variance, then what results in it is the chi squared distribution with n minus 1 degrees of freedom. And we can prove the second part here. So think about it this way. If we can assume the two are independent. Now, if we consider this n minus 1 times s squared divided by sigma squared, where the sigma squared is the variance, that should be from 1. It shouldn't be from 0. Again, a typo. Sorry. So I'm going to change that to, Yeah, I wrote so much material last night that I was very tired after finishing it, so I didn't proofread it. And now we can see what happens. Okay, so if we calculate this so we can translate or you know, separate this into two parts. There is xi minus mu plus mu minus x bar. And then we separate this into here. And well, the justification for this leap is a little bit, it requires a little bit of analysis. If you calculate this open, here arises something and here arises something, you can get this to conform to that. I'm not going to go into detail there. But what you see from here is that this is N01 divided variable. So this is he squared with degree of freedom 1. Oh, there is still 1 0 missing. I think it was used here. I think it was used here that these are N01. These are N01 distributed variables. This is N01 distributed variables. There are N of these, and then 1 is subtracted. Then this gives us the result. But the problem, of course, is that it's now using the sub theorem that I claimed that it was using. This is not actually completely accurate. The last part here of the theorem is not completely accurate. I don't know what I was thinking when I was writing it. It doesn't actually go because of this. The reason for that is that, you know, this has each of these, I mean, is included in this as xi over n in this part sum. Xi over n is included in here. Xi over n is included in, sorry, for each I is included in here. So this is not a very good proof here, but the intuition is the same here. Intuition can be thought of as coming from this. So you have n degrees of freedom because this is there's n independent variables here, but then you're subtracting 1 degree of freedom here by taking 1/n of each of those variables. And this is not, I don't think this proof is correct that it proves actually this. It would prove if the subtraction theorem part was correct, but it wasn't, so neither is this. But the intuition is the same. So you have n independent variables here, and then this kind of removes 1 degree of freedom because a part of each of these is included in here. So I'm sorry about this. This is a little bit wibbly wobbly, this theorem here. It doesn't matter. The main part is that you understand that this is, in fact, it is true, but the proof is bad. Yeah, sorry about that. You can see that this is the part of the material that I didn't have in the previous year, so it's not honed out very well yet. So, all right, let's move on. So we have this, it's chi-squared distributed, and now we're going to talk about this confidence intervals. So the theory presented in this previous section gives us, given a random variable, some indication of the distributions of, oh, that should be hat, not hat x, but bar x. Distribution of the sample mean and sample variance, and how they are estimators of actual mean or actual actual expected value and actual variance. So by estimator, we mean that if we calculate these or get these are random variables because they are dependent on what sample we take. When we take a sample, we take several. Yeah, bar as in, yeah, it should be bar here. I'll fix that too. Right. The bar x. So if we have a random variable and we take a sample, we get the mean of x. So, you know, mean of the sample. Of course, the mean always has a It depends on the size of the sample, but I'm just assuming it's some n. So these are random variables that closely or more closely resemble the actual variance and expected value than just you can deduce from a single sample or a single point. And when we say estimators, then we mean that their expected values, it's unbiased. They're unbiased estimators, means that they're as random variables, they have the expected value. The mean has the expected value of mu, and the sample variance is the expected value of sigma squared. It's really important to understand that estimators are random variables whose values are then realized in a particular sample. So they can vary. When you take another sample, you get slightly different estimator here and here. We said that they are unbiased estimators. We already proved them. When we calculate these estimators, we call this estimation. So we want to estimate parameters of a distribution. We could estimate other parameters, but in this course, we only focus on these two, the variance and the expected value. And the idea is that you come up with an empirical value for a parameter from a sample. So it's an empirical value, meaning it's actually measured from the real world by taking a sample. And then we try to figure out whether this is, value, actual value, which we don't know. Really, I mean, philosophically speaking, it's not just that we don't know. It doesn't even necessarily exist in the sense that it's only part of our model. Because we build a model of randomness, in which case we think that some variable it is a random, we think of it as a random variable. That's part of the model. It's all in our heads or on a piece of paper that we've written. It's a model of the real world. The real world phenomenon could be something else entirely. So we take it as a random variable, and it doesn't have per se, it doesn't have a actual expected value or variance. But what we do mean by this is that you can think of it as there is a model that most closely resembles the reality or most accurately describes the whole population. So when we estimate it, we come up with a value, and we want to somehow figure out that, okay, is this a good value, or where would the actual value be if we could measure it? So we can say nothing definite about the actual value, but what we can do is we can give probabilities that the estimator is within some range given this calculated statistics. So when we, for instance, calculate the sample variance, then we can't say that the actual sample variance is like this, but sorry, the actual variance is like this. But what we can say is that, okay, we got this sample, and if the actual variance is like this, then this sort of sample has a certain probability of being in certain range. That is what we can do. So these ranges that we will come up with, we call them confidence intervals. And confidence interval has two parameters, basically. It's the sample that we take, which basically has n as a variable, as a parameter. So the larger or smaller sample, and then the confidence level. And we say 1 minus alpha confidence level in this because we are usually giving the confidence level as the alpha is usually given as the tail end probability. So when we say alpha is 0.05, then we talk about 95% confidence interval. So that's 1 minus alpha, so that's 0.95, and then often we talk about percentages. So don't be confused by this. So the confidence is 95%, but the alpha, which is the cutoff limit, alpha meaning the alpha level is 1 minus that. It means it's those that still could be out there. So if alpha is 0.05, there's still a 5% chance that we are wrong. So if we have a parameter theta, in this case, it's either the expected value or the variance, and this is the actual parameter of the distribution. We say that this 1 minus alpha confidence interval is a random interval, and now these hat theta 1, hat theta 2 are sample dependent random variables, such that the probability that the actual parameter is in fact between these two is 1 minus alpha. So if this 1 minus alpha is 95%, so with 95 confidence level, we can say that the real value is between these two. And it doesn't say that the probability, it's really important to understand. This is the one I warned about, that you need to turn your mind a little bit backwards here. So it doesn't say that in the real world, it's a 95% chance that this is where the actual value is. What it says is that if the actual value is in this range, we have a 95% chance of getting this result that is in this, that looks like this. So if it's in this interval, then we have a 95% chance of getting this. So in terms of conditional probabilities, and this is a conditional probability. So the condition here is that if our distribution is what we think it is, and the parameter is here, then the probability of getting, so this is not the random variable, these are, right? So let's go through the theory so maybe you can understand it a little bit better. Here, the realized sample gives us two random variables, theta 1 and theta 2. And the random variable here is that interval. So that interval shifts, And what we say is that if we take 1,000,000 of these, then 95% of those samples result in an interval which actually contains the actual value. We don't know what the actual value is. We can't even deduce it, even if we have that 1,000 of these results. What we can know is that, okay, whatever the actual value is, 95% of those contain the actual value. On average, I mean, if we take very, 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 very many of them, if we take infinitely many of them. And it's all hinges on the assumptions that the distribution is in fact the sort of distribution we think it is. In most cases, a normal distribution. And herein lies another problem that you will see here. One of my big objections against this statistical analysis, or not objection against it, more a warning against trusting it too much, is that we are making multiple assumptions that certain distributions are normal. And then we are piling these assumptions on top of one another. And if at any point the assumption breaks down, then the given probabilities will be wrong. Let's move on. Higher the confidence, the wider the interval. So if you want 100% confidence, then your interval will contain all possible values, all the real numbers. Alpha equals 0 means that there is no room for error. Then anything can happen. These are random variables, so if we assume that they are normal distributed, then they can be any real number. Yes, its probability is very small that it's very large or very small, but it's still it's still possible. So absolute certainty will never ever be attained. On the other hand, if you don't need to be too particular, you said the high alpha, you're willing to accept 50% chance of being wrong, then you might get very narrow confidence intervals, meaning that you can say something more accurately, but you have a higher chance of error, or you can say something very, very inaccurate and you are very likely to be correct. This is like a equivalent to the uncertainty principle. This alpha is often called the risk level. So if we want risk level 0, that's a risk of being wrong, if you will. I would contend that that's no, the hat above the, okay, yeah, that's a good question. The hat above the theta. The hat here means simply that as opposed to this actual theta, this is an estimation of theta. So when we use the hat, then the hat above a variable name is often, this theta is not a random variable, it's some parameter. So this hat theta here means that this is something that we calculated from the sample, and it's an estimation of this theta. So we have two estimators, theta 1 and theta 2, and this interval here gives us some kind of range where this resides with a high probability. So the bar is used for average over a sample, whereas the hat here is used as a separator between the actual theoretical value and something that we calculate from a sample. So alternatively, we could, instead of saying S squared for the sample variance, we could write it sigma hat squared. So that would be more equivalent here. But it's a good question. Yeah. So let's talk about confidence interval of the expected value. So if we have an we know that the expected value can be estimated by the sample mean, the bar X, right? That's the average. We have a random sample here. We know, let's assume for now that we know the variance, but we don't know the expected value. So in this case, the sample mean has the same distribution, the same expected value, but a smaller variance than the actual variable. So variance goes down, expected value stays the same. We normalize this, the normalized variable has a N01 distribution. So let's say that we are talking about a risk level alpha, and we fix 1 minus alpha to some level. We first determine this thing called Z alpha divided by 2. And let me give a justification for why it's Z alpha divided by 2. And before any confusion arises. So let's say that this is my, again, this is not symmetric, but let's say this is my distribution of normal, this is my normal distribution. Now let's say for argument's sake that this is a 0, 1 normal distribution. So we have these blackened regions here, or these regions that I colorized. These are the less probable regions. Their total probability is alpha. That's the risk level. So we can be wrong in one of two ways. Our value is much bigger or much smaller. So I have alpha divided by 2 and alpha divided by 2 on both sides. I have alpha divided by 2 on both sides. So the total amount of probability mass that resides in this uncertain region is alpha. So that's why the total probability mass here is 1 minus alpha. And that would be Z alpha per 2, Z alpha over 2. So we have these are our limits, right? From the N01. So you see from this picture that the probability that normalized sample mean is between these two values is 1 minus alpha. And if these are from a 0, 1 normal distribution, right? So now we solve this for mu. So so this is in the middle. So we have to multiply both sides by sigma over the square root of n. So we multiply this by first by sigma over square root of n, this by sigma over square root of n. So we get this and this minus here on the other side. Then we are left with x minus mu on the middle, and then we shift these minus, put everything to minus, then changes the direction, but it actually this remains as it is. And then we add to both sides, or we can subtract from both sides x bar, and then change the signs. So mu is between these two values if we solve it. So this is the confidence interval. So this is the probability that the actual mu is between these two values is 1 minus alpha. And understand now that this is that if mu is fixed and this is the sample we get, then whatever the mu is, then this sample, this is the random variable here. This is in fact a random variable. We are just adding this. This depends on the actual sigma and the n. So it's 1 minus alpha. This may be a hard thing to understand, but the random thing is not this thing in the middle, so that it's not an interval where the side, the end and the beginning are fixed, and then the thing varies there. Instead, the mu is fixed and the ends vary like this. And we get a random sample, and in 1 minus alpha is the probability that this interval lands somewhere, so that the mu is somewhere in the middle. So this is what we call the confidence interval estimator. It has two parameters, and this is the theta 1 hat, and this is the theta 2 hat. So it's got a random component, which is the sample mean, and then this is simply derived from both the two parameters, the alpha and the n. And then the cumulative distribution function from the n01 normal distribution is this z alpha per 2, and the value should be 1 minus alpha per 2, alpha over 2. So now you know how to calculate the estimator. Now I'm going to add to Friday's examples a lot of these examples where we do this, and because we have to skip today many of these examples, so we don't have that much time. This is sometimes known as the 100 times 1 minus alpha % confidence interval. I think this is a little bit of underestimating your intelligence. I can say 1 minus alpha confidence interval, and then if it's 0.95, I can say 95% confidence interval. If alpha is 0.015, then this is the 95% confidence interval. Alpha here denotes the probability mass that remains in the tails, like I draw in my picture I showed you just. So when n is large, sigma squared is known, and the sample is of good quality. The central limit theorem guarantees that this sample mean is very closely normally distributed. That's why this theorem is often used even when the variables themselves are not known to be normally distribution. But this is a standard practice, but like I said, it should be viewed with caution because the n should be large, the sigma should be known, and the samples should be of good quality, randomized. Because I mean, the theorem here assumes that this underlying variable is normally distributed, but it in fact really doesn't have to be normally distributed. It's enough that this the sample mean is normally distributed, and it's pretty closely normally distributed if the sample is high quality. So here's an example. A machine fills soda cans with liquid. The variance is known to be 9 milliliters squared. A sample of 50 cans shows an average of 325 milliliters of liquid per can. So 95% confidence interval. We can calculate it now that we know the standard deviation. We know that the variance, the standard deviation is the square root of that. So it's 3 milliliters. The confidence interval here, we calculate the 0.05 Z value, which is 1 minus 1/2 of that, so that's 0.975, and determine that Z alpha over 2 is approximately 1.96. So we get 1.96, that's the Z value, times 3 over the square root of 50, n was equal to 50. And then we subtract this and add this to this to get this sample mean 325 to get this confidence interval. So this is the sort of thing that we can conclude is that, okay, we got this sample of 325, average 325 with this variance. 95% of the time, the actual, this is the sort of a sample we would get 95% of the time if the actual mu was between these two values. So if we repeat this, kind of 50 sample random, then 95% of the cases are such that this interval would contain. So this can be transferred to the other direction as saying that, okay, we conclude that it's about 95% chance that this roughly in this region is where the actual expected value of the liquid amount of liquid that is put in the cans is. But you know, this hinges on there's the assumption that under this is the probability under the assumption that everything is well designed here. Okay, let's move on. It's not terribly common for us to actually know what the variance is. Well, you can use, I've used this a number of times. So for instance, in MATLAB, we could use the command norminv, and if this is the value, then here we had the value was 975, so we get 0.975. So that would be, for instance, in MATLAB. You have to look at, I mean, you are free to use any software you like, but you're free to use any software you like, but please look up, consult the manual, whichever software you're using. I can put some examples. Maybe in Friday's examples, I put some examples in MATLAB and also examples from Python. If I have the time, I'll do that. I'm a little bit pressed for time here currently, but yeah, it's a good question. I'll put also a manual table which you can use. I haven't yet done that, but I have a table of that distribution. Can be also found at the end of the finished material. I can put a link to the finished material on the web page. You should be able to access it online anyway, the finished material. So it's the tables for the normal distribution and the chi-squared distribution and all that, they are there. But I'll add them to my Moodle. But you see here, the assumption was that we know the variance. It's not actually terribly common for us to actually know what the variance is, isn't it? I mean, if you think about it, usually we have nothing else about the distribution except that we know we have some assumptions about what kind of distribution it is, but then everything else is empirical. We have to determine it by sampling estimate the sample variance, estimate the variance by using sample variance. So very often we have to use the S squared instead of the sigma squared because we don't have the actual variance. The problem here is that now it introduces another random coefficient into the formula. So instead of having just one random variable, which is the sample mean, we now have the sample variance, which is also a random variable. So if we use S squared in place of sigma squared, the randomness in the estimate increases. So the confidence interval becomes wider. So we can no longer assume that the normal distribution assumptions hold, because it's no longer just normal distribution. That's what we're going to be talking about now. So we need a distribution that would better capture this estimator behavior. And luckily there is one. And again, looks a bit hard. And don't stress, I'm not going to want you or expect you to be able there's something wrong here. That shouldn't be T minus Q. Well, I'm going to fix this. I'm sorry about this. So don't worry about that. This is the Euler gamma function. There was some mishap here. So we have the gamma function appear in this student T distribution. It's called the student T distribution. It's just T distribution. We denote it by Tn. And it has a certain relatively complicated density function that depends on n. But forget about this formula. Understand here that what is this latter part here? That approaches, as n approaches infinity, this approaches e to the t squared over 2. E to the minus t squared over 2. So what happens here is that this, and this part will, this will in fact, when n approaches infinity, can be shown that this approaches the density function of the normal N01 normal distribution. So as you would expect, if we have an infinitely large sample, then the normality assumptions will hold, no questions asked. But if the sample is smaller, then this is a wider. So you can look it up. There are pictures, you can find the graphs of this T distributions density function. It's flatter when n is small, and it becomes more and more starts to resemble the normal distribution as n grows. And this captures the idea. We'll see shortly that the T distribution is what emerges instead of the normal distribution. So if we have a small sample, then the curve will be flatter than in the normal distribution. So let's assume, here's an example. I mean, the T distribution is symmetric around the 0. So the thing it's not immediately obvious that it's symmetric around the 0, but if you think about it, this only part where this T appears is T squared. So it's definitely going to be symmetric around 0. So if we have T with n degrees, with 18 degrees of freedom, and we need real numbers, T1 and T2, we can look it up from the table. Again, here's an example here. We want this T from between T1 and T2, so we find the symmetric value T1. So again, the distribution I'll try to draw a slightly flatter distribution than the normal distribution. So this should be symmetric, but it's really not. Just like in the normal distribution, but this is supposed to be somewhat flatter. We are looking at this, but we have to look it up from a table or use software. And here is an example. We can use MATLAB. We get 2 different values. We can get the first one, this one. This one, we need 95 here because we need to solve this. So it's f t minus 1, but it's doubled because there's for the same reason, there's it's not T2, it's T1. So again, the half comes from here and the 1/2 comes from here. That's why it's 95. So we are only calculating, we're only going to calculate one of these sides, and then we get this T1, and then the other one is at the other sides, and we get this. So there's 5% above T1 and 5% below minus T1. That's why we have 95. So, sorry, I'm sorry. Yeah. 5%. There's total of 10%. We can calculate these values. The MATLAB has tinv, and then it has a parameter of the actual degrees of freedom. Again, look up from a table. If you have a book, old school statistics tables have these T tables, and they have this chi-squared tables, and they have the normal distribution tables. But we probably use software in the modern day. The important theorem here, if we have a 0, 1 distributed variable and we have a chi-squared distributed variable and they are independent, then a random variable, which is z over omega per n, omega over n, the square root of, not omega, sorry, the square root of w over n. So z divided by the square root of w over n, then this turns out to be Tn distributed random variable. So in particular, if we have a random sample with a n mu sigma squared distribution, then this, instead of being 0, n0, 1 distributed, it has a t distribution with n minus 1. And this one we don't prove. We won't prove this. This is quite involved. But given this, we can easily prove that, and it comes from this. So let's rewrite the latter part as this part as u over w over n minus 1. And we can, if we write u as this is n0, 1 distributed. It has the actual variance appears here, but, and the actual expected value appears here. But remember that this is in the used in the estimator, so there can be the expected value can appear here as an unknown. The variance appears here, but if we are taking this w and we mark it as n minus 1 times s squared over the sigma squared, we remember that this was, we claimed, there was a theorem which we gave without actual proof, but we claimed that it's well, we gave a proof, but the proof was a bit bad, but still, if we believe that theorem, then this has a chi squared n minus 1 distribution. And if we take the square root of that, then what emerges here is that we can eliminate this sigma squared. We take the square root, it becomes sigma, and then there's a divisor of sigma here at u. So those two are eliminated, and what we in fact end up with is simply this, and it's Tn minus 1 squared. Sorry, Tn minus 1 distributed variable. So oh, that shouldn't be T there. Why is there T there? I'll shortly explain. You asked how much of this can we understand, or should you understand? Well, when you say understand, it's a bit hard question. How much of this do you need to understand? If you are just going to use the formula and calculate the formula, where you learn the formula how to calculate the confidence interval, you don't have to understand anything. What I want you to understand is, if you know, I would want you to understand everything. Obviously, it's not going to happen. But what I want you, what is the most important thing to understand, barring, you know, besides the fact that you can then use the actual formula, is the fact that we are building on some assumptions, and then we're tearing down these assumptions, and we come up with new things that introduce more randomness. Like, for instance, you have to understand that initially, when we assumed everything is normally distributed and the variance is known, then we were able to come up with a nice formula for the confidence interval. But then we have to relinquish the assumption that the variance is known. We have to throw that away because we don't know the variance. We know the sample variance, but not the actual variance. And that makes the confidence interval bigger. So we understand that we are introducing a little bit more randomness, because instead of knowing the actual variance, we are using the random variable, which is the sample variance. And if you understand that, then you will be able to understand why this formula, even though it looks pretty much the same, why it's somewhat different, and why you are using different table, why you are using different distribution, not the normal distribution, but the t distribution. You have to use the t distribution and not the normal distribution, because the t distribution is flatter, especially for smaller n, so it accounts for the fact that this is not perfectly normally distributed, because it's a random variable and not just actual variance. That much I hope you understand. The actual symbols here are not that important. What is more important is this, why we are doing this. All right. So we have, this looks the same as the confidence interval calculation. Let's move on to the actual confidence interval. This looks almost exactly the same as the confidence interval that we had when we know the variance, but we don't know the variance, and now we are using the sample variance, s squared, and this is the square root of that. And here we use t, which doesn't have the n01 normal distribution, instead has the t distribution n-1. So understand this. If you calculate the estimator knowing one variable, in this case, knowing the one parameter, knowing the variance, then you get a tighter estimator. And if you don't know the variance and you're using the sample variance, which is a random thing, then you have a wider estimator. Okay? This is the thing that you need to understand here. So if you use the purely theoretical concept where you would know the variance, you get certain interval. And then when you use the sample variance, you get a wider interval because of the nature of randomness that was introduced, the unknown sigma. So this is exactly the same formula in form, but it has a different variable here and a different variable here to account for the fact that we do not know the variance. That much I hope you understand. Okay? So you don't have to learn this formula. I will provide this formula for you in a cheat sheet. But I hope that you understand when to use this formula and when to use the other one. And why. That's more important. Why would you use different formula in different situations? So the thing about this, that very large n, the Tn is very close to n01. So as with large n, s squared is also with large n as it's an unbiased estimate. So it's very close to this actual variance. The difference, though, is not immaterial. I mean, think about it. If n is 100 and alpha is 0.05, these are 0.05 is a very common risk level. I don't know why, but it's like, 1 in 20. So if you calculate the Z alpha over 2, meaning with known variance, in the formula where you know the variance, the factor would be 1.645. The t distribution with 100 degrees of 99 degrees of freedom on the other hand, gives a level of 1.66 for alpha. So it's about 1% difference. So, you know, it doesn't seem like much, but, you know, think about it, 1% difference in the interval, it just might be material. So it's not completely immaterial which one you are using. And of course, when you don't know the variance, you should also always use the t-distribution. But I warned you in the beginning that this gets complicated. This is the most complicated part of the course, is these estimators, because it requires you to think in a reverse manner in some way. So that's hard for many people. There's another example. In speed control by the police, the speed of 31 cars was measured in kilometers per hour for 10 minutes. 10 minutes doesn't matter. The average speed, now here we use small lowercase x because this is the actual measured value. We got 97.4 kilometers per hour, and sample variance turned out to be 98. So the square root of this. So what determine the 95% confidence interval for the average speed. I'm not going to go through this example. You would punch in the numbers here, s square root of n. So that would be the square root of 98. That would be the square root of 31. And this you would look at the t-inv of I think it's 0.9, what was I looking, 95, 0.975, because you are eliminating 2.5% at both ends. And then you subtract that and add that to that 97.4. I'll add that example into the Friday sessions examples. But now we don't have time to go through this. Here's another example, one that we might look at a little bit more closely. A study was designed that uses sampling. It's often required to consider how large n needs to be achieved. So how large you need the n to achieve a certain level of accuracy. So if you want your confidence interval to be narrower, and you have already determined your confidence level, alpha. So you want 95% confidence level and you want a narrow interval. Then you need a larger sample. If you want to narrow your interval, you need a larger sample. So I don't know, you often see poll numbers given and they give you a margin of error. Like, you know, they've gotten like, let's say they say that some party has 20% people, 20% of people would vote for this party. And then they say that, you know, the margin of error is 1.5%. Then what they really mean is that they have usually it's a 95% confidence interval. And then in 95% of the cases, the that would be the sample mean. They mentioned the sample mean. And in 95% of the cases, you know, it's within 1.5% of that. So they're actually giving this Z alpha over 2 times sigma over n squared. Or in fact, what they might be doing is they're giving from the t distribution. They're calculating from the t distribution because they don't know the variance. They don't know the variance in there. Okay, so you want this is your width. This is your margin of error, if you will, this A. So this is how much from this is the 1/2 of the interval is done like this. So if you want that 1/2 one-sided error, you know, on the interval to be less than or equal to A, You solve this for n, then n has to be larger than z alpha times sigma over a squared. So here's an example, our liquid samples have zinc content assumed to have the distribution 0, 0.3. This is really ridiculous because the zinc content cannot be 0. Well, in any case, the confidence interval alpha, this shouldn't be 0. You can't use normal distribution for zinc content to have an expected value 0 and some variance, because that cannot happen. It has a lower limit. Probably there's a typo here. So using 95% confidence interval, we have Z alpha at 1.96, and to come up with the estimation error of at most 0.05 milliliters, we need a sample size, and then we can calculate that we need n greater than or equal to 139. So this is a rudimentary example of the sort of analysis you need to make in order to design a study. This course doesn't give you the tools to design your own studies. There are more advanced courses for that, but it does give you the idea that if you read a study that has done statistical analysis and they talk about estimation errors and error margins and so forth, then you should be able to recognize those things and understand that the nature of those numbers. They're not giving you 100% certainty, or they can't give you like 95% probability that we are absolutely correct. That's not how it works. All right, so this is hard. We'll look at this. We'll go through this. This is best handled by looking at a lot of examples. So we'll do that on Friday. But we're pressed for time, so we need to talk about the variance as well. So this is this is about as hard as it gets. Next week's topic will be somewhat easier, assuming that you've understood this. So I'm going to put a lot of effort on Friday to go through the examples and we'll figure this out. So here's a random sample again with normally distributed variable. Notice how whenever we talk about and develop this theory, we always assume that the underlying random variable is normally distributed. That's the tall order here. And that's the place of critique is for this theory, is that the underlying variable might not be normally distributed. Granted, this thing applies with a very large sample, even if it's not normally distributed, provided that it's somewhat regular, has a reasonable expected value and reasonable variance. However, it's something that you need to be a little bit suspicious about whenever you see something. So we've established here that this, when you calculate the statistics of the sample variance, then you can transform it into a chi-squared variable with n-1 degrees of freedom. But the problem, of course, here is that this sigma squared is not known. The variance here, the actual variance is not known. But we can, because we know this, and there's only one unknown here, we can use this to come up with confidence intervals for the variance. So this chi-squared is not symmetric. So this time we need to calculate two different values. And again here, we need to calculate two different values. That there's an alpha over 2 probability for being here and alpha over 2 probability of being in this long tail. Because it's cut off at 0 and it has this kind of a hump shape here. We can solve this probability that because this is chi-squared, so this is this in the middle here, n-1 s squared and so forth has a chi-squared distribution. So we have a known distribution, and we have the limits which we can then figure out from the actual chi-squared distributions values. We can calculate them with software. Remember, I mentioned that. That's, I think it's, was it chi-inv or where was it? I think it had, I had it above here. I had mentioned it. That's T in, and I think, sorry about this. Huh. Don't I have it here? Yeah. Yeah, it's this command gives us, so it would be he2inv, and we would have this degrees of freedom, which is n now is unknown, and if we have here 90, I'm just gonna go back to where we were. Sorry, jumping up and down. So we determine these W1 and W2 if it's alpha over 2. So if alpha is, for instance, 0.05, then we would calculate 0.025, 0.975, right? We'd calculate this, and we would get what would come out would be W1, W2. That would be the vector that comes out. If you use MATLAB, for instance, that's how we get W1 and W2. And now we notice that if we solve this for sigma squared in the middle, then we get that the sigma squared is between these numbers, and minus 1 s squared over W2 and n minus 1 s squared over W1. So you know, here we're dividing by these unknowns instead of multiplying like in that other confidence interval. And if this probability is 1 minus alpha, so this gives us the theorem that if we have a sample of mu sigma squared, then the confidence interval in the interval estimator of the parameter sigma squared, or the variance estimator, interval estimator, can be calculated with n minus 1 times the sample variance divided by W2, and the upper limit is n minus 1 times the the sample variance over W1. And then this W1 and W2 are the alpha over 2 limits of the chi squared distribution. That's why this comports to the 0.01 here, 0.025 here, and this to the 0.975, or graphically W1 and W2, because that's this part and that's this part, right? So here's an example. 30 glass panels were measured for thickness, and notice to have this sample variance of 0.0645. We assume the thickness is normally distributed, determine the 95% confidence interval for the variance. It should be noted that other than in the calculation of the sample variance, the actual sample mean doesn't appear in this formula at all. Of course, it appears when you need to calculate the sample variance because it's how they are around the mean, but the mean doesn't. If we only know the sample variance and not the mean, the mean is not needed separately from the sample variance. Because I mean, if you look at the expected value, there we need not just the sample mean, but also the sample variance. So often we then estimate the sample variance first. Another confidence interval, one more topic, for relative proportion. So, I mean, let's think about a binomial distributed variable. So it's a repeated Bernoulli experiment with probability P. Think tossing a coin or throwing a dice and calculating how many sixes you get. So you have a certain probability of getting a certain result, and you calculate how many times you get that result. So you either get it or don't. And in the frequentist interpretation, P, the probability in this binomial distribution, is the long-term relative frequency of success in this repeated experiment. So if you do it many, many times over, then if you do it n, where n is very large, then roughly n times P is the number of times we get it. So the binomial distribution is really grounded on this frequentist approach, and it's really, you know, the distribution if we think about it this way. So if we have a random variable, which is the one experiment where we have this probability P, so it's the probability P of getting heads, or, you know, 1 minus P of not getting heads. And let's say that we don't know what this P is, and we need to estimate this P based on experimental data. So in this case, the expected value of Y is P. And it's also the expected value of a sample mean of Y if we take many repetitions. We throw the dice, we calculate the number of sixes, and we divide that by the number of rolls we made, and we get the average, the expected value, or sorry, no, the sample mean, which then has the same expected value as that. Alternatively, we can think of this as being an occurrence of a binomial distribution, distributed variable X with n repetitions and P probability, which we are then dividing by n, right? We're repeating this n times. This sum here is binomially distributed. So this is the same random variable. This is a binomial distribution, NP, but we're dividing it by n. So we know that the random variable, which is the average, is an unbiased estimator of this P, because we know that the expected value of Y, you know, the expected value of the sample mean is the same as the expected value of the variable itself. And remember, Y has two outcomes, 0 and 1, and so it's easy to see that if P is the probability, then P is also the expected value of Y. So we know that, remember that it's the same variance as Y has, but divided by n, because we have n repetitions. And what is the variance of Y? Well, it's P times 1 minus P. Well, you can think of this from the from the binomial distribution. Bernoulli distributed Y is in fact the same as binomial distributed with 1 and P. So its variance is P times 1 minus P times n, but when n is 1, so it's just this. So in this case, Y is Y, the sample mean of Y, it has n repetitions. So this has a variance of P times 1 minus P over n, because it's the variance of Y over n. This is the average. So as you see, we get a larger and larger n, we get smaller and smaller variance, and a more and more accurate description of P. And by central limit theorem, if n is very large, then the sample mean is roughly P, you know, it's roughly normally distributed with expected value P and variance P times 1 minus P over n. It's roughly, I mean, when n is large, then this is not roughly normally distributed. So, if we have a binomial distributed variable, then we can have the confidence interval for the probability P in this binomial distribution at confidence level 1 minus alpha by simply taking this hat P, which is the estimator for the probability P now. That's why we use the hat. So the small, the lowercase p with hat would indicate the particular value, and the uppercase P with this hat is the estimator, which is the random variable. This is the typographical convention that we are following here. So here, that average minus then it just exactly like we had, but this here is the sample estimate of the, I mean, using the normal distribution approximation, this would be the variance roughly. So we get this estimator. And for binomial distribution, this is so close when n is macroscopically large, so we're talking about hundreds of repetitions, then this is so close to the normal distribution that this is actually a very good confidence interval estimator. And we can notice that this will really rapidly go towards zero, really. After this P is starts establishing. Here's an example which we could calculate, would be, we have a flight route, has 140 scheduled flights per week. On a particular week, 124 are flown without incident. We should calculate the 99% confidence interval for the probability that a random flight is flown without incidents. So it's 100, I mean, the estimator for P is 140 over 124, and then we would use the normal distribution. We can come up with a, knowing that this n here is 140, so we should come up with the estimator for this, and we'll do that on Friday. All right. So here, this is pretty much all there is to these estimators. So this is very formula heavy, but these formulas are really, I'll go back here up. There are only two forms of formula that you need to remember. Actually, only one, and then everything else follows from that. But I'm suspecting that that's not how you're going to view it. So let's go back here where we develop the confidence interval here. So really, the confidence interval stems from of the expected value stems from this, that this is N01 normally distributed, and then from this we know that we can solve this for N01 distribution, this Z alpha, and we can come up with this limits here in the normal distribution, and then solving this for mu in the middle, we get the confidence interval. So this is the first formula that you need to memorize. And of this formula, you should probably remember also that it comes in two flavors. This is the pie in the sky, if you will, formula in which the variance is known. It has that sigma there. But then there is the less certain one where the variance is known. Instead, we are using the sample variance as its estimator. And in this case, you have to understand that this is a variation of the same formula. It's derived in the same way, but we have a slightly different distribution because of the fact that now the variance is a random variable. So here comes the t distribution, a more flat distribution than the actual normal distribution. The normal distribution is the theoretical construct, and when n grows to infinity, then this t distribution will resemble the normal distribution. But when n is not infinitely large, then we will use the t distribution, and this is exactly the same formula, except that it has the s here and the t here to denote the uncertainty. So understand when to use which. Basically, in real life, you always only use this with the t distribution. You don't use the other one because you don't know the variance. Then, for variance, the other formula which you need to understand is that this is a He squared distributed. This is the equivalent of the normalized standard, the normalized sample variance. And it has the He squared distribution. And here is the sample, using the sample variance, here is the estimator of the confidence interval. And where the n factors in is calculation of these, again, calculation of these W1 and W2 from the He squared, and I already gave that, that's the He in, I showed you there, of these levels, and then this width of this distribution depends on the n. And you see, The thing about this is that because this W1 and W2 are divisors of this, then the weird thing is that the wider this distribution is, the narrower this confidence interval estimator is. Because these divisors will be larger values. That's how it goes. So we'll show some examples of it. These are the two things from this lecture that you need to remember. And then there was this binomial distribution. It has the same flavor here. It's except that this is a specific case where it's easy to come up with an estimate. All right. I'm going to stop recording here. If you have any questions, ask them now. I'm a little bit pressed for time to quit now because I need to take a break. Any questions? When you say you're worried that there would be too many theories, what do you mean by too many theories? But I mean, yeah. No, you don't have to memorize the theorems. Remember, I mean, think about these theorems as follows. The theorem is a theoretical justification for using a formula. And you have to understand the theory to the extent that you know how to determine the confidence interval. This is the hardest part of the course. You're worried, and I understand that you're worried because this is the hardest part of the course. I warned you about this, that this week's material is the hardest part of the course. I'm going to stop recording now a little bit. We can still continue discussing.